Good evening, everyone. Am I audible to everyone? Okay. Let's wait 1 or 2 minutes for others. So let me start today's session. So this time we will cover the week 2 topics. I hope you have already watched the all videos of the week 2 content from the portal. And today we will discuss some of the exercise question regarding the week 2 content. Okay. So in between, if you have any doubt, you can ask. And this question will help you in solving the assignment. So accordingly, solve the assignment before the deadline. So, okay, before starting, myself Harsha, I am from IIT Tirupati, a research scholar. So let us start the session. Let me share the screen first. Is my screen visible? Is the screen visible for everyone? And am I clearly audible? In between, if you have any technical problem or anything, please let me know.
Yes, madam, visible. Hello, visible, madam.
Okay. So, first of all, we will just go through very quickly, we will go through the contents that are all covered in the last week. So, I am not going to explain what are all the contents. I will just go through, just revisit whatever the content covered. So, the week 2 started with the equivalence relation. So, equivalence relation, the last week we ended in the equivalence relation, and then using the equivalence relation, we can have a partition of the set. So we started the week 2 with the equivalence relation. And we all know what is an equivalence relation. It is reflexive, symmetric, and a transitive relation. And using the equivalence relation, we have a partition of the set. So we have studied what is a partition of set using the equivalence relation. Okay. So next thing what we have studied is mapping or function. So what is a mapping or function? Mapping or function means a map from a set A to a set B such that for any A in A, there exists a f of A in B. That is the mapping. So in this, we have studied 1-1 mapping or 1-1 function, and the next on-to function, and 1-1 plus on-to means bijective mapping. Okay. So I hope you all know the concepts here. And okay, then we have studied the composition of function. What does the composition of function means? If a map f is from A to B and G is from B to C, then G composition f from A to C. Okay. So in between, if you have doubt, you can ask. And then we have studied what is a permutation. Okay, permutation is a bijection from a finite set A to the set itself. Okay. Then we studied what is enumerable set, what is a finite set, what is a countable set. Okay. Okay. So binary operation star. Next thing that covered in the last week is binary operation star from the Cartesian product of the set A cross A to the set A. That means a binary operation is a rule which associate for any element in A cross A, there exists a star of AB which belongs to the set A. That is a binary operation. And then we have studied so many concepts like groupoid. We have studied groupoid, semi-group. I'm not going to the definition of all these. Semi-group, monoid, group, etc. Okay. So basically, these are all the main things that covered in the last session, last week. So let us go to the problems. So first problem is related to an equivalence relation. So I will give a relation on a set A, and we need to check whether it is an equivalence relation, symmetric, transitive, reflexive, any of this. Okay. So question is, suppose R is 4, 3, 6, 6, 5, 3, 3, 5. So this relation R is defined on the set 1, 2, 3, 4, 5, 6. So we need to check whether it is an equivalence relation, whether it is a reflexive relation, symmetric, or transitive. Sorry, my internet is a bit slow. Okay. Whatever I am writing, it is coming at, it's lagging. Okay. So we have the set S 1, 2, 3, 4, 5, 6, and you can see how the relation R is defined. R is defined in a such a way that 4 is related to 3, 6 is related to 6, 5 related to 3, and 3 related to 5. So first of all, we will check whether it is reflexive or not. So can anyone say whether it is reflexive or not? Is this a reflexive relation?
Madam, no, madam.
Okay.
No.
Can you tell the reason?
Because 3, 4, the element 5 are is in the set, but not reflexive, not
I
mapped
think
onto the
Siddharth
set.
is saying about the symmetricity, right? 4, 3 is in the relation R, but 3, 4 is not. This condition, okay, this condition implies it is not symmetric. So before that, let us go to the reflexive condition. What is the reflexive condition? For any element in the set S, for all A in S, A should belongs to R. Is this true here? No, it is not reflexive. Because, for example, we can take any element, 1, 2, 3, any of the element. So we have 1, 1 does not belongs to R. Okay. In the same way, 2, 2 does not belongs to R. So this kind of elements are not in R means it is not reflexive. Clear? Now, what about the symmetricity? Already one of you have answered. Is this symmetric? No. Okay. So he has already given the example because 4, 3 is in R, but 3, 4 does not belongs to R. You can see. Four, 3 belongs to R, but 3, 4 does not belongs to R. What is the condition of symmetricity? If AB is in the relation, then BA should also be in the relation. Here, that condition is not satisfied. We are having an example here. So, what we can say, this is not symmetric. Now, third condition. What is this? Transitive. Whether it is transitive or not. Okay. The reason is 4, 3 and 3, 5. Okay. 4, 3 and 3, 5 are there, but 4, 5 is not. Okay. We can see the element 4, 3 and 3, 5 belongs to R. We can see in the set R, 4, 3 and 3, 5 belongs to R. Okay. But if it is transitive, what we need? AB and BC belongs to R should imply AC should also belongs to R. Here 4, 3 and 3, 5 belongs to R, but 4, 5 does not belongs to R. So by the definition of R, we can say 4, 5 does not belongs to R. Okay. So no transitive also. So obviously this is not reflexive, symmetric and transitive. This implies it is not equivalence relation. Okay. So actually, none of the options is true. Okay, let me give one more option here. None of this. Okay. So the answer is E. None of this. Is the question clear? Answer clear for everyone? Any doubt in this? This is the very basic thing to check a relation on a set is equivalence or reflexive, symmetric or transitive. So this is just the applying the definition and we will see. Any doubt here? At any point, if you have doubt, please ask. Okay. If you don't have any doubt, let's move to the next problem. So, second question is, if A is a finite set, containing 4 distinct elements, that is, cardinality of A is 4. Okay. Then the question is to find the number of relations on A. So the options are given 6, 9, 2 power 16 and 512. Okay,
16,
the
ma'am.
set A is given. Given it is a finite set containing 4 elements. That is, A contains 4 distinct elements. So the question is to find the number of relations on A.
It's 2
So,
power 4 only.
anyone can answer this one? What is the correct answer out of these 4 options?
Madam, 2 power 16,
16, 2 power 6.
2 power 16. Option C.
Um,
2 power 16.
No, it's 2 power 4.
any
It's
answer?
2 power 4 only, no? Because power set only is the relation. So 2
It
power
is
4.
not 9. Okay, let us see.
2 power 16, ma'am.
2 power 16.
Power 16.
Sorry, I was not able to hear what you were saying in between. Can anyone talk just to check my audio?
2 power 16, ma'am. Option C. Option C. 2
Can
power
anyone talk
16.
just to check my audio? Are you able to hear me?
Two power 16.
Okay, okay. Okay, so let's go to the problem.
2 power.
So given that cardinality of A is 4. Okay. What is the definition of a relation? Okay, 2 to the power of 60. Yeah, option C. This is the correct answer. Okay, let's just solve the question. So, cardinality of A is given as 4. Okay, so what is a relation? What is the definition of a relation? Relation is a subset of A cross A, right? Is it correct? Relation is a subset of A cross A. Okay. So, what does number of relation means? Number of relations is same as number of subset. So, each subset of A cross A is a relation. And relation is defined as a subset of A cross A. So, number of relation is same as number of subsets of A cross A. Okay. So, here, what is the number of subsets of A cross A?
$16.
Sorry, I don't know whether you people are speaking or not. I don't know whether it's a problem with my side. Gauri, are you talking?
Yes, ma'am.
Okay, sorry, I'm not able to hear you all, I think. Just give me 1 minute. Can anyone talk now?
Ma'am?
Huh?
Ma'am?
Yes.
Okay, sorry, I'm not able to hear. I think some problem in my side. Okay, as of now, let us use the chat. There is
Okay.
some problem in my side, I think. Okay. Okay, here, what we are having is number of subsets of A cross A. So, number of subsets of A cross A is given by 2 power 16, right? So, okay. Two power cardinality of A cross A. This we have covered in the last session. If A is a set having n elements, then number of subset of A is 2 power n. So we have given the proof also in the last session. So here, number of subset of A cross A means 2 power number of elements in the A cross A. Here, what is the number of elements in A cross A? It is 16. Okay. So it is 2 power 16. Clear? So the answer is C. Any doubt in this question?
No, ma'am.
Yeah, so number of, okay. Okay, I hope everyone understood, like Vinayakam, this is clear, right, for everyone? So the only thing we need to note is the relation is a subset of A cross A. So to find the number of relations, it is enough to find the number of subsets of A cross A. Okay, so let's go to the next problem. Which of the following are examples of group? Okay, so we have studied what is the definition of the group. Okay, so the question is to find which of the following are group. So first of all, before going to the answer, let us see what is a group. Group G star. When will we say a set G with a binary operation star a group? What are all the properties?
Commutative property, associative property.
Associativity. First of all, it should be closure.
Yes.
Okay.
Closure.
Closure properties, associative property.
சென்ட் அடிச்சுட்டு போற பத்தியா நீ குளிச்சதானே அந்த சென்ட் எதுக்கு அடிப்ப
And third one is existence of identity
And inverse.
and existence of inverse. Okay. So let us go to the option by option. So first of all, Z plus. What about this? Is this a group?
Set of all integers.
Yeah, set of all integers with operation addition. So is this a group?
Yes, ma'am.
Yes, it is a group. So first of all, closure property. If I'm taking two integers A and B, then A plus B also belongs to Z, right? This is what is meant by closure property. So first condition is satisfied. So the associativity means A plus B plus C should be equal to A plus B plus C for all A, B and C in Z. Okay. So for any integer, if we are taking A, B, C, this addition, like in whatever the order we are adding, that does not matter. So associativity also false. Now, what is the identity here?
Zero is
0 is a
Zero.
addition
Yeah.
identity.
0 belongs to Z. And for any element A plus 0 equal to 0 plus A equal to A. This is the condition for the identity. Okay. For all A in Z. So it satisfies the existence of, that is, there exists an identity in Z. Now, what about the inverse? If we are having an element A in Z, what is the inverse of A under addition?
minus A.
Minus A. So minus A also belongs to Z, and A plus minus A under the addition, we are getting A plus minus A equal to 0, which is the identity that we have already found. Okay, which is equal to minus A plus A. Okay, so Z plus is a group. Clear? Now let me ask a question. Z under multiplication. Is this a group? Yeah, no, it is not a group. For example, okay, what Siddharth is saying is, for any element, if we are taking, it does not have an inverse.
Inverse.
For example, I am taking 2 in Z. Then the possible inverse is under multiplication, the identity will be 1. So the possible inverse is 2
1 by
into 1 by 2 is usually will be equal to 1. But this 1 by 2 does not belongs to Z. Okay. So this is not a group. Now let me go to the next option. Next option is R plus. Okay, what about R plus?
set of all. It's a group.
Yeah, it is a group. This is R means set of all real numbers with the binary operation addition. Okay, it is a group.
It satisfies all the conditions.
Yeah, so it is just like the integer group. Z plus we have studied that it is associative, closure property is satisfied, identity, inverse, everything is there. So here also the same results hold. So it is clear that addition of two real number is a real number. That means closure property is satisfied. Yeah. And the second one is associativity. That is clear. Whatever the order we are adding the elements, it does not matter, right? So associativity also false. So again, what is the identity here?
1.
Identity under addition.
0, 0, ma'am. Sorry.
Okay. 0 is the identity under addition. And inverse is same as. If A belongs to R, what is the inverse?
0.
Inverse.
There exists minus.
Yeah, minus A.
Minus.
Yes, correct. Minus A. For A belongs to R. Minus A also belongs to the real number such that A plus minus A equal to 0, which is equal to minus A plus A. So clearly it is a group. Now the third option is Q minus. What is Q?
Set of all rationals.
Yeah, Q is the set of all rationals and under the operation subtraction. Is this a group?
Yes, ma'am.
Any other opinion?
No, no, ma'am.
No, correct. It is not a group. So let us see what is the reason. First of all, the closure property is satisfied or not?
Depends upon the number. Depends upon the number. It satisfies.
Yeah.
Closure property, it satisfies.
Yeah, because any AB is rational number we are taking, then A minus B, obviously it is a rational number. Okay, so closure property is satisfied. Now, we need to check associativity. So, does associativity is satisfied? For example, let us take some example. This is a subtraction, 1, 2, 3 in Q. So, what is 1 minus 2 minus 3? Minus 1 minus 3, right? Okay. Now, what is 1 minus 2 minus 3? Which is equal to 1 minus minus 1. 2. Now, does this associativity satisfies?
No, ma'am.
No, right? Because A minus B minus C, that is A minus B minus C not equal to A minus B minus C. Okay, this condition not true always. Okay. So this is not associative. So one condition does not hold means it is not a group. So it is not a group. Now, again, next thing is 2Z under multiplication. What is 2Z? Two Z. Two Z is the set of all even integers. That means 2 times Z. So 2 times set of all integers means it just gives the all even integers, right? So it includes all minus 4, minus 2, 0, 2, 4, etc. This is our 2Z. Okay. And in the same way, we can write 2Z plus 1. What will be 2Z plus 1 then?
It's an odd number.
Yeah, this is the set of all odd numbers. Minus 3, minus 1, 1, 3, etc. It will go. Okay. So 2Z union 2Z plus 1 is our integer set. So we can see it as a partition. Z. Clear? Okay. Now let us come to the question. The question is 2Z under multiplication.
No, it's not a group, ma'am.
Yeah, obviously it is not a group. We already proved that Z under multiplication is not a group. Here also the same way we can say for some 2, if we are taking 1 by 2, the possible inverse 1 by 2 is not there in 2Z.
Not exist.
So it is not a group.
If they give 2Z under addition means we can say it is a group.
Yeah, 2z under addition is again a group because two even integers if we are adding, again it is an even integer. And yeah, associated with clearly holds. And the identity 0 is also there. For any even integer 2n, the minus 2n inverse is also there.
Okay.
So yeah, it is okay. Let us write that also. 2z under addition is a group. So if you want, you can just verify all the property. Okay. So anyone has doubt in this one? Like how to check the group conditions?
No.
Okay, so let us move to the next question. Okay. Before going to the next question, let us just see some condition to check whether a function is surjective, bijective, or injective. So, if I am giving a function f, suppose f is a function, real function. Okay, that is, it is defined from the real number to real number. So, first we will see the vertical line testing. So if we have a function from R to R, we can represent the function as a graph, right? So the graph of f is, we will take set of all x and the corresponding the value f of x, set of all x f of x such that x in R. Okay. Now we can plot this x f of x in the plane R2. This is the plane R2. Suppose I am just plotting. Suppose a map f is given. I don't know whether f is a function or not. Suppose my f is as shown in this. Okay. Whether this figure represents a function or not.
It's a function.
Okay. So let us see what is a function. Function f from R to R. If f is a function, can f have two images? You know what is mean by image, right? That is, for any element x, f of x is said to be the image of f. Okay. So my question is, if there exists an x in R, is this
Then
f of there exists an f of x? So is this f of x is uniquely defined, or there exists some f of x and some other point? That is, there exists. Does there exist b a and b not equal to a such that f of x equal to b and f of x equal to a? Is this condition possible? 1 minute. Okay, some of you have already answered. Okay, let us see. Is this condition possible? No, right? But here in the graph, we can say for some particular point, I'm taking this point, it has two images here and here, right?
Yes.
So, what this says is it is not a function. This is what is called vertical line test. If a graph of a function is given, we will just draw vertical lines. I mean, all possible vertical lines. If the line intersects at 2 points or more than 2 or more points, then it is not a function. Okay. Is that clear? Vertical line test.
Okay.
Okay. To check a function f is, to check a map f is a function or not, we just need to check whether the vertical line intersects with the graph at only 1 point or not. If it intersects at only 1 point or less than 1 point, means 0 point also, then it is a function. Otherwise, it is not a function. Okay. Now, let us go to the horizontal line test. First of all, let me draw the graph of f of x equal to x square. So, this is the graph of f of x equal to x square. Okay. So, question is this f11? Is the map f of x equal to, this is a function, right? We can check the vertical line test. Each vertical line, if we are drawing, it intersects exactly 1 point only. Okay. So, it is a function. Yeah. Now, is this a 1-1 function?
Yes, ma'am.
Yes.
Okay. Let us say what is the definition of 1-to-1 function. What is the definition? Can anyone say?
Number of elements in A have number of images in B.
See, we cannot say number of elements in A if A is infinite. Like in countable case, we can say number of elements and all. Other than that, we have a very basic definition for 1-1-ness.
If f of x is equal to f of y, then x is equal to y.
F of x equal to f of y, then x should be equal to y, right? Or its contrapositive statement, x not equal to y implies f of x not equal to f of y. So the second statement, what I am writing here is the contrapositive of the first statement. That means what it actually means is for distinct elements x and y, distinct image should. Now, does this map f of x equal to x square satisfies this condition? For example, let us take x equal to 1, y equal to -1. What is f of x? What is f of x here?
1, 1.
1. And what is f of y?
1.
1. Now, what does this imply? Is this 1-1 or not?
It's equal. So it's not 1 to 1.
Yeah, it is not 1-1 because here f of x equal to f of y, but x not equal to y. Clear? That is,
Yes.
both 1 and -1 have same images. In the same way, 2 and -2 will have same images under the map f. So f is not 1-1. Okay. So this is how we will use the horizontal line test. So what does the horizontal line test means? We will draw the horizontal line. Okay. Horizontal line means this horizontal lines intersect at 2 points of the graph. Here at this point and this point, any horizontal line will intersect. So if the horizontal lines intersect at more than 1 point, then it is not a 1-1 map. Okay. Is that clear for everyone? So, if horizontal line intersect with more than one point in the graph, then it is not 1-1. Okay. If the horizontal line intersect with more than one point, it is not 1-1. Now, I will give you one example. So this is the graph of x cube. Okay, it's not exactly. Okay, x cube will come something like this. So is this 1-1 or not? Like just using the horizontal as horizontal line test, then what you can say whether it is 1-1 or not? If you are drawing a horizontal line here, at how many points it will intersect? Suppose I am drawing a horizontal line here. At how many points? Any horizontal line I am taking. You can check with any horizontal line. At how many points it intersect? Yeah. Okay. So this is a 1-1 map. G of x equal to x cube is 1-1. Because it intersect at only one point. Now, okay, what is the question here? If horizontal line does not intersect, then 1-1 no.
Hello, madam. Can
Yeah,
we test with vertical line?
See, vertical line we can use whether it is a function or not. Here, if you are using vertical line, we cannot conclude anything about, see, in the x square case also, if I am drawing a vertical line, it intersects at only one point, right? From that, we cannot conclude anything. Here it is not 1-1, f of x equal to x square. But here it is 1-1. But in both the cases, vertical line will intersect at only one point. So that means using the vertical line test, we cannot conclude about the 1-1 ontoness. Only thing is whether it is a graph or not, we can. Sorry, whether it is a function or not, we can check. Clear?
Okay, okay. Thank you.
Coming to this question, I think what he is asking is, if horizontal line does not intersect, then whether it is 1-1 or not. So basically, if we are drawing a graph, like if the domain is R, obviously horizontal line will intersect it. Now, if I am having something like this, okay. So here also, if I am taking any horizontal line, either it will intersect at one point and not intersecting at one point, means any point, right? In this case also, what we can say is it is 1-1. For a distinct point, we have distinct images. But in this case, whether is this onto map? So the graph is like this. Let me draw this graph. So this blue curve represents the graph. Okay. Clearly from the graph, we can see it is a 1, 1. Even though all the horizontal line does not intersect, some of the horizontal line intersect and some does not intersect it. But it is 1, 1. Okay. Now, can you say anything about the ontoness here?
How we can check, madam, without graph 1, 1 or not?
Sorry, can you repeat?
How we can check the function is 1, 1 or not without graph?
Okay, without a graph, that already covered in the lecture, right? Means what is the definition of one-oneness, ontoness? That we have already given. That is f of x1 equal to f of x2 implies x1 equal to x2. If that condition is satisfied, it is 1, 1. Okay. And the ontoness means whoever not talking, please mute yourself. See, okay, let me give the definition first. One-oneness means, suppose if, here, this graph, I am using just real lines. Actually, the function can be from any domain, means some finite set to finite set and all. Here I am dealing with the functions on real lines. So let me, in general, give a function f from a to b. So definition, f is 1, 1 if f of x equal to f of y implies x equal to y. Okay. Now onto means range of f should be equal to b. That is, for all b in b, there should exist an a in a such that f of a equal to b. Is the definition clear? Ontoness definition. If f is a map from a to b, if we are for any b in b, if we are able to find an a in a such that f of a equal to b, then it is said to be onto. Clear? Okay, so you want the name of this function. Okay, suppose it will be a exponential function. F of x equal to a power x it will be. Or you can say e power x or something. Some kind of exponential function graph will come like this. Okay. So just use the definition of ontoness and see whether this graph is a or the function is a onto map or not. Okay, let me give one more hint. If I am taking any negative real number, okay, does there exist a element x such that f of x equal to that negative real number? Suppose some -1 belongs to R. Does there exist a x in R such that a power x equal to -1? So here a is some positive number. Okay, the graph a power x will be like this. A is some positive number. So, for example, suppose a equal to 2. If you want a simple case, let a equal to 2. 2 power x equal to -1. Is this possible? This is not possible, right? Yeah, whatever he has written, it is correct. 1, 1 means horizontal line intersect at most 1 point, and on 2 means horizontal line intersect at least 1 point. So here, if I am drawing the horizontal line here, see this horizontal line, this does not intersect with the curve, right? So this is not on 2. What does this mean? This graph or the function f covers only the positive y-axis. That means the image lies on the positive y-axis only. So whatever the point I am taking here, so whatever the point I am taking x here, x f of x will be like this. That means this is our f of x. Okay, this f of x is always greater than 0. If I am taking some x here, suppose here I am taking x, this is my x f of x. So corresponding f of x is this one. Okay, here also f of x is positive. So whatever the point I am taking in the x-axis, f of x lies in the positive y-axis. Okay, so f of x is not negative. That means for any negative real number, we cannot find an x such that f of x equal to that real number. Is that clear? So this is what exactly horizontal test says. So if we are drawing a horizontal line, then if at least at one point, if it intersects, then it is on 2. Okay. So 1, 1 means horizontal line intersect at most 1 point, and on 2 means horizontal line intersect at least 1 point. Is this clear? Is both the statement clear for everyone? What is the reason? I don't know whether I made it complicated or not. Is this clear? How using the horizontal line test, how we can examine the one-oneness and on-two-ness? Any doubt here?
Please justify onto using graph at
Okay,
least 1 point.
Okay. Suppose I am taking some function like this. First of all, I am taking just a graph. Don't think about the function. Okay. I don't know what is the function is. So whether this is a function or not, how we will check vertical line test, right? So using that, is this a function?
Yes, it is a function.
Yes, first of all, f of x is a function. Because if I am drawing any vertical line intersect at only 1 point. So f of x is a function. Okay. Now, what onto by definition says is, so our function is from R to R. Okay. So by definition, for all x in R, there exists a some A in R such that f of A equal to X. Is this definition clear? Is this definition clear?
Yes, yes, yes.
Yeah. So, for example, I am taking X as a negative number, say it is here. Okay. So, my question is, does there exist a real number A in R such that f of A equal to X? Suppose, I suppose that some A exists. Suppose A is somewhere here. But what is f of A? F of A is going to the upper side here, right? That means f of A is here, which is positive number. So whatever the A I am taking in the positive x-axis, you can see that f of A is always in the positive y-axis. Whatever the A value I am taking in the positive x-axis, you can say f of A is always positive because this is the point A f of A. Okay. If I am taking some other element B here, so corresponding graph, here it is the B f of B. That means this is our f of B. Okay. Now, if I am taking A somewhere here, again, here is the f of A f of A. That means this is our f of A. Clear? So, whatever the A value I am taking, all f of A, so for all A in R, from the graph, we can see that f of A is always positive. Okay. That is f of A not negative real number. So, we cannot say, means we are getting that f of A is always positive and not a negative real number. So, whatever the image we are taking, it is a positive real number. So, we can say there does not exist any real number which maps to the negative y-axis. Is that clear? So, for example, if I am taking the horizontal line here, it does not intersect with the graph. Okay. So, this is the equivalent condition of saying that it is not onto. Clear?
Hello?
So, again, yeah.
So for onto, there must be a line on the negative side, na? Function must be in both positive or negative.
Can you repeat?
Madam, for onto to be
Onto.
true, onto to be true, so
Ah.
function must be on positive side as well as on the negative side, na?
See, onto to be true means the range should be complete R. Okay, that means positive and negative should be there because map is defined from R to R. So f of R should be complete R. But here f of R is only positive real axis, right?
Okay, okay, okay.
So that is why the onto-ness does not hold here. So the same thing if we are explaining graphically, we can say if we are drawing a horizontal line here, it does not intersect with the graph. Clear? So this is, we can say equivalently, if the horizontal line does not intersect with the graph, then it is not onto. Clear?
Yes, 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 madam.
Okay. Okay, the question is, what if horizontal line does not intersect the function? Okay, this only I was explaining. If the horizontal line here it does not intersect with the function, so it is not onto.
Madam, how to check the function whether it is onto analytically without a drawing graph?
Yeah. Okay. Sorry, ontoness, right? Suppose f is given from A to B. Okay, a map f is given from a function is given from A to B. F is onto if range of f equal to B, or equivalently we can say f of A should be equal to B. That is, what is f of A? F of A means set of all f of x such that x in it. That means we are taking all elements in A and the image of that elements under F. If that set, if that collection is same as B, then it is onto. Or again, we can say for all D in B, if there exists a in A such that f of A should be equal to B. So this you can see as the, I think this is the best definition. So if I am taking any
Means,
element
madam,
in,
means that is it correct? Let me know. Means that the A domain should completely must utilize the B domain, na? That is onto.
yeah, there does not means there should not be some B which is not mapped under F. That means if we are mapping the
Okay,
F1
all elements should be mapped in B domain, na?
Means all elements in the B, all elements in B should be mapped under F.
Under F, okay.
Yeah. So that is what he is saying. If I am taking any element in B, there should
Madam,
be some
please.
S.
Madam, please explain with some example.
Okay, okay, I'll explain.
Okay, thank you.
Now, okay, let us go to some simple example. F is a map 1, 2, 3, 4. X, Y, Z, P, Q. Now, my map is 1 is going to X, 2 going to Y, 3 going to Z, and 4 going to P. Okay. Now, by the definition, so F is a map from A to B. What the definition says, every element in B should be mapped under F. Here, if I am taking Q, let Q in B. Does there exist some T in A, some element in A such that f of T equal to Q? That is the answer for this question. Question is, I am taking an element Q. Okay, Q is not an arbitrary element, the fixed element Q here. Is there any element in A mapped to Q? You can see the mapping here, right?
No.
No, right? Because 1 is mapping to X, 2 is to Y, and 3 to Z, 4 to P. There is no element which is mapping to Q. Okay, so this is example of a not onto function.
Not onto.
Yeah. So f is not onto, because there exists some element in the B which is not mapped under the F. Okay, so this is an example of not onto. Now, let me give an example.
If madam, hello. If 4 is mapped to Q, then what? Is it onto?
Which one?
If 4 is again mapped to Q, if 4 is mapped to Q, it
Okay,
is mapped to
suppose-
P and also
First of all, is this a function? If 4 is mapped to P and 4 is mapped to Q, then is this a function?
No.
No, it is not a function. Okay,
Yes, ma'am.
4 cannot map to Q. Clear?
Madam, it is clear, ma'am.
Yeah.
But when given in a question in terms of function of x, in terms of x, how to check the function whether it is on to? How to check? Picturally, it is okay, ma'am.
Okay.
How to check the, suppose given function is in terms of x, how to check this is onto, whether it is onto or not?
So basically, if such a functions are giving, mainly it will be some kind of linear function ax plus b, or f of x equal to some cx square. See, this is, or f of x equal to e power x. Like this function you are, right? So if this kind of function, if you are getting this kind of function, basically the function will be from R to R. So the main thing to check is, again, I will say the horizontal line question. So we can just see how the graph will be. For example, if I am taking f of x equal to ax plus b, it will be some line. It is a linear function, right? So we can say, we can check with any horizontal line. Any horizontal line intersect the graph. So it is a onto method. But if I am taking cx square, again, cx square will be something. Okay, something like this it will be. Here, the horizontal line test fails for ontoness. Here, the second horizontal line does not intersect with the graph, so it is not onto. So, if some functions like this, it comes, it just depends on the function, what kind of function you are getting, and from which domain to which domain it is defined. Then only you can say, for example, suppose f from z to z, such that f of x equal to 2x, and f from z to 2z, such that f of x equal to 2x. Okay, here I am giving the same function f of x equal to 2x, but the function mapping, first function mapping from z to z, and second function mapping from z to 2z. So here, just looking at the function, then only we can say whether it is onto or not. For example, first one, is this onto? Just seeing the definition of function, you can see whether this all the 2x covers the full set or not. How do you think f of x equal to 2x from z to z? Is this onto?
yes, it is onto.
Is it onto? Okay, then what will be the pre-image of 1? See, for example, I'm taking any x in Z. Okay. So what is f of x? F of x equal to 2x. It is always an even number. Okay. But our codomain is Z. This set contains both even number and odd numbers. Correct? Our set contains even and odd numbers. But this F maps to only even numbers. What does that mean? This odd numbers is not mapped under the set. Okay. For example, suppose 1 in Z. Okay. By the definition of ontoness, what we want, our question is, does there exist a x in Z such that x is mapped to 1 under the function f? If this condition is satisfied, we can say f is onto. Okay. Okay. Is this condition is satisfied? The last sentence. Can you find an x in Z such that f of x equal to 1? Any answer?
No.
No, right? Because the possibility, like f of x is 2x. F of x equal to 1 means 2x equal to 1. But 2x equal to 1 only if x equal to 1 by 2. But this 1 by 2 does not belongs to our domain set. Okay. So whatever the odd number I am taking from this set, it is not an image of any element. Okay. So that is why f is not onto. Then any doubt in this one? First one, why f is not onto? Is that clear?
Yes, yes.
Okay. Now, coming to the second one. Now, is G is onto? Is this G onto or not?
Yes.
Yeah, in this case, G is onto because we are restricting our codomain to only even integers. Okay. Now, G is from Z to 2Z such that G of x equal to 2x. Okay. Now, if I am taking any element from 2Z or any y in 2Z, y will be some form in 2n. It is an even integer because y is a even integer. So, y I can write it as a 2n. Okay. So, what will be the g of n? G of n will be, by the definition, g of n will be 2n, which is equal to y. Clear? That is, we started with an element in 2Z. We found an element, an integer in Z such that g of n equal to y. Okay. This implies g is onto. This happens because we eliminated all the odd integers from the codomain. So it is a onto method. Clear?
Okay.
Okay. So whenever you have a function, just see from where to where it is defined and what is the definition. And actually, if you are doing so many questions, like so many practice questions, then you will be able to understand quickly to which element it is not mapped, or does there exist an element to which G is not mapped, and so on. So So just go through some. Yeah.
ये ठीक हो जाएगी लिंक ठीक दिया गोपाल
Sorry.
कृष्ण ये तो कौन पोस्ट सकते तभी नहीं चाहिए सका वर्षा गोपाल अयो मेरे इसमें नेट पे चांगन नस्ता होने क्या बोलते कि सुनाऊंगा भी नहीं इधर सुना तो उसमें जो
हेलो हेलो
Sorry.
एबीसीडी हेलो
Uh,
आप क्यों डिस्टर्ब कर रहे हो यार आप?
okay, I hope he was not asking any doubt. Okay, in this oneness and ontoness, do you need more example or any other doubt?
No, madam, clear. Okay, carry on.
Okay, then. Let us solve one more problem related to the oneness only. Question is, let f from A to B and G from B to C. So, if G composite F is okay. Before that, what does this surjective means?
Surjective means onto.
Onto, and injective means
1
1. Okay, so this is the alternative term for 1 and onto. So I hope you know this. So the question is f from A to B and G from B to C is given. So the composition G composite F is well defined, right? Okay. G composite F will be defined from where to where? What will be the domain of G composite F? F from A to B and G from B to C. Then G composite F from will be which set to which set?
First A function is operative and then G function is operative.
Yeah,
That
first
I understand.
First F function is operating. G composite F means first F is operating. So F is mapped from A to B, right? Okay. So first of all, the domain should be then A because F is the function to be operated first. So the domain of G composite F should be same as the domain of F. So after mapping F, we will go to, that means if we are taking an element X from A, F of X will go to B. Okay. Now, to that F of X, we will apply G. That means G composite F of X equal to G of F of X. Okay. So, X is a element of A. Then F of X is a element of B because F is mapped from A to B. Now, what will be G of F of X? F of X is an element of B means G of F of X will be an element of C. Element of C. Okay. So,
G of F is mapped to A to C.
yes, G composite F should be a map from A to C. That means from domain of F to range of G or codomain of G. Clear? Now, the first statement is if G composite F is surjective, then G is surjective. So we need to check whether this is true or not. Okay. What do you think? Is this true or not?
True.
True. Yeah. Let us go to the proof. What is given? G composite F is surjective. And we know that G composite F is from A to C. So, G composite F is surjective. Then by definition, what we can say? What is the definition of the surjectivity? For any C in C, there exists A in A such that G composite F of A equal to C. Is this clear?
Yes, yes.
Yeah. So what is G composite F of A? G of F of A. Okay. Now, let B equal to F of A. I am taking this F of A, this F of A. I am notating this by B. So what we can write is G of B equal to C. Okay. Where does this B belongs? Which set this B will belong? B equal to F of A.
F of A. So it is in
Ah.
A domain.
No. F of A means a map from A to B, right?
This
So
is the element
A,
of B.
yeah, A belongs to A and F of A belongs to B. That means F of A equal to B belongs to B. So what we are getting here is for any, we started with some C. For any C in C, we got a B. B equal to F of A in B such that G of B equal to C. That implies G is onto or surjective. That means for any C in C, we know that G is a map from B to C. For any C in C, there exists a B in B such that G of B equal to C. Yes. Any doubt here? Why this is surjective? Is this clear?
Yes, ma'am. Yes.
Okay. So we are just using the definition of the surjectivity. For any map, there should be a pre-image that we have proved here. So G is surjective. Clear? Whoever not talking, please mute yourself. Okay. Now, second statement is if G composite F is injective, then F is injective. So here again, we will start with the given condition G composite F is injective. Okay. So G composite F is from A to C. What does the definition of the injectivity says? G composite F of A1 equal to G composite F of A2 okay. This is the definition of the injectivity, right?
Right. Right.
Yeah. Now, what we want to prove is F is injective. So, how we should start? F is a map from A to B. Okay. I am taking two elements, suppose X and Y in A. And F of X equal to F of Y. What we need to prove? We need to prove that F is injective. So, if F of X equal to F of Y, we need to prove that
X equal to Y.
X equal to Y. Okay. Now, F of X equal to F of Y. That means F of X and F of Y are same elements in B. Okay. Now, I am applying G to this both sides. That means G of F of X should be equal to G of F of Y. Clear? I am just applying G to both sides. Okay. So, what is G of F of X? G composite F of X. And what is G of F of Y? G composite F of Y. Okay. Now, we already know that G composite F is injective. So, what does this imply? X equal to Y, right? Is this okay? Because G composite, yeah, G composite F is injective. So, G composite F of X equal to G composite F of Y implies X equal to Y. So, we proved it. We wanted to prove that X equal to Y. So, we proved it. So, what we are getting is F is injective. Clear? Any doubt? Any doubt in this condition? Means both statements?
No. Okay. Okay, ma'am.
Actually, you can see this statement as a standard result. Means you can just remember, like if G composite F is surjective, then G is surjective, and G composite F is injective, then F is injective. Now, the third statement we will see. If G composite F is bijective, then F is, this is actually a very trivial statement because we already proved the two statements. So using that, we can easily prove this. So how we can prove the statement? Yeah, the question is there possible G is 1-1? Actually, it need not be true. These two statements are true. Like if G composite F is surjective, then G is surjective. But G need not be injective always. In the same way, F need not be onto also. So I will give you one example. Before that, let us prove this result. So this is very trivial result. So G composite F is bijective. Okay. What does that mean? It is surjective and injective. Okay. So if G composite F is surjective, we proved that G is surjective. This we already proved. And it is injective means F is injective. So what we are having is G composite F is bijective. So bijective means it is both injective and surjective. So it is surjective and injective. So from the first result, we got G composite F is surjective means G is surjective, and G composite F is injective means F is injective. So 3 holes. Okay. Any doubt here? Anyone has any doubt here?
No, okay.
Okay. Good. So, okay, let me give one example. So I have map F from I have two maps F from A to B and G from B to C. A is set to 1 and B is set to 1 to C is set to 1. So first of all, is this a function both F and G? Is F a function?
Yes.
Yes. And G?
Yes.
Yes, it is also function.
Yeah, both the F and G are functions. Now, what is G composite F? G composite F is from A to A, right? Sorry, A to C. But here A and C are same set 1. Okay. So this G composite F is defined as G composite F of 1 equal to 1. Okay, clear? So G composite F is an identity function on the set A, we can say. Is that clear, this definition, G composite F?
Okay, okay.
Okay, so from this we can say that G composite F is surjective and because it is a bijection and it is injective also. Okay. So if G composite F is surjective, then we proved that G is a surjective mapper. Is this clear from the example? Here G is surjective, right?
Yes.
But what about F? Is F surjective?
No.
No. Okay. So if G composite F is surjective, we can only say G is surjective. F need not be surjective. That is what this example says. So someone asked about that question. In the same way, here G composite F is surjective, G surjective, but F not. And what about here G composite F is injective map? Is this G an injective map? Is this G11?
No, G is not injective.
G is not injective. What about F?
F is injective.
Yeah, we proved already F will be injective. So from figure also we can say F is injective, but G is not. Okay. So the above statement is true in that sense only because the second one, G composite F is surjective, only G is surjective, F need not be surjective. And if G composite F is injective, only F is injective, G need not be injective. Clear?
Okay, okay.
Okay. Okay, now let us do one question from permutations. A permutation rho is given by BC and sigma is given as DE on the set A, B, C, D, E. Then question is, What is rho sigma? So the permutation rho is given as BC. What does that mean? B is mapped to C and C is mapped to B. And sigma means DE. That means D is mapped to E and E is mapped to D. The question is, what is rho sigma? Rho sigma means rho composite sigma. So first let me write rho as A, B, C, D, E. So what is the image of A under rho? Rho is given as cycle BC. So what will be the image of A under rho? Okay, leave it. What is the image of B under rho? Where B is mapped?
C.
Okay, B is mapped to C and C is mapped to
D.
B. Okay, if we are given such a cycle like this, B is mapped to C and C is mapped to B, and whatever the remaining element, it will be mapped to itself. That means A is mapped to A, D to D, and E to E. Okay. This is what this representation means. Clear? Now, what is sigma? Sigma means A, B, C, D, E, and A. Okay, under sigma, to where this A is mapped?
Map to A,
Yeah, A is
A.
mapped to A and B to
B,
C to
C,
and
C.
yeah, D to
E,
E.
D to E and E to D. Okay,
D.
clear. Now the question is sigma rho. Sigma rho is same as sigma composite. Sorry, rho sigma. Rho sigma is same as rho composite sigma. Okay. So to find the rho composite sigma, we need to find the value of rho composite sigma to each of the element A, B, C, D, E. So we will see what is rho composite sigma of A. What is rho composite sigma of A? Rho of
A.
sigma of A. Yeah, rho of sigma of A. Sigma of A is, sigma of A means A mapped to A under sigma. So it is rho of A, and rho of A means A to A, right? Which is equal to A. Clear? Now, what is rho composite sigma of B? First
C.
apply sigma. Can you repeat? Rho composite sigma of B is rho of sigma of B, right? Which is equal to rho of B. Sigma of B means B mapping to B. Okay, so rho of B. Now, what is rho of B? Under rho, B is mapping to C, right? Now, rho of B equal to C. Okay. Now, rho composite sigma of C. We can do directly. Sigma, under sigma, C is going to C. And
It is a B. It is a B.
yeah, C is going to B. It is B. Now, rho composite sigma of D.
D.
D under sigma, D is mapping to E. And
And
under
it is
rho,
D.
E is mapping to E, right? This rho of sigma of D. So, sigma of D means E. And we need to apply rho to sigma of D. That is rho of E. Rho of E is E. Clear? Now, rho composite sigma of E. What is this rho composite sigma of E?
D.
Yeah, sigma of E is D, and rho of D is D. So it is D. Is this clear? How we are writing all this composition? It is just taking the composition of the permutation. It is same as the function composition. Okay. So we are getting all the image of A, B, C, D, and E. If we are writing it as rho composite sigma equal to okay. So let us just copy this from. So A is mapped to A, B to C, C to B, D to E, and E to D. So the order is A, C, D, E, D. A, C, D, E, D. Clear? This is our row composite sigma. And if you want, you can write it as BC, cycle BC, DE. Okay, because B is going to C and C is going to B. So it can be written as cycle BC, and D to E and E to D. It can be written as the cycle DE. Okay, so this row composite sigma can be written as BC, DE. The remaining element A is mapped to itself. Okay, is this clear? Any doubt in this?
No, clear, madam. Thank you.
Okay. Okay, now next question. So given a permutation, so the permutation is given on the set 1, 2, 3, 4, 5, 6, and it is defined as this. Okay, so the question is to find the equivalent form of this permutation. Okay, I will give you 4 options: 1, 3, 2, 6, 4. Okay, here we have we are representing it as the product of cycles. So you know what it actually means. If 1, 3, 2 cycle is given, means 1 is mapping to 3, 3 is mapping to 2, and 2 is mapping to 1. So the question is to which of this representation the given permutation is equivalent? Can anyone say what is the answer? Any idea which is the correct answer out of this? The only thing is we need to write this representation as the cyclic representation, and then to find the matching representation.
1632. 1632.
1632. Okay, let us just write this. So the question, it is given as 1, 3, 2, 1, 3, 2, 4, 6, 5, 4, 6, 5. I am writing it as the cyclic representation. So cyclic representation, I am starting with the first element 1. Okay. Now, what should be the next element? Next element should be the element to which 1 is mapped. 1 is mapping to which element? Here.
1 is mapped to 3.
Yeah, third option. 1 is mapping to 3. So, in the cycle, next element should be 3. Now, next element should be the image of 3. What is the image of 3?
6.
Image of 3 is? In this permutation, what is the image of 3?
2.
Yeah, 2. Now, the next element should be the image of 2. What is the image of 2?
1.
Yeah, 1. But we are starting with 1. So, the cycle is going to repeat again, right? 1 is going to 3, 3 is going to 2, 2 is going to 1. So, this cycle is closed here. Okay. So, we covered 1, 3, 2. Now next element is 4. So let us see the cycle containing 4. So I'm starting with 4. So next element should be the image of 4. What is the image of 4? Yeah, 6. Image of 4 is 6. And what is the image of 6?
5.
Yeah, 5. What is the image of 5?
4. So it is closed.
4. Yeah, it is again closed. So we are writing it as the product of 2 cycles because it now covered all elements 1, 2, 3, 4, 5, 6, right? All elements are covered. Okay, so this is same as the third option. So answer should be option C. Clear? So this is how, if we are getting a permutation, this is how we will write it as the product of cycles. Okay. Now,
Okay.
yeah, any doubt in this?
No, okay. Thank you.
Okay. Now, next question is, okay, again a question of one. So question is a map given from R to R and given f of x equal to 5x square minus 8. We have already seen so many examples like this. And the question is to check the 1, 1 and 1, 2. So first of all, is this 1, 1? Is this 1, 1?
Yes, ma'am.
Reason?
Reason is
Okay. My question is, what is the image of 1 under f? What is f of 1?
-3.
F of 1 is -3. And what is f of -1?
-3, ma'am.
Okay. Now, is this 1, 1?
Yes, ma'am.
How can it be 1, 1? Means I'm taking 2 elements, 1 and -1, distinct element, but both are mapping to the same element -3. Correct? So, what is my condition?
It is on to now. It is on to.
First, let us see about the 1, 1ness, then we will come to on to. Okay. So, f of x equal to f of y implies x equal to y. Then f is 1, 1. Okay. Here I am taking x equal to 1, y equal to -1. And the f of x equal to f of 1 equal to -3, which is same as f of -1. Which is f of y. Okay. So f of x equal to f of y. But x not equal to y. Correct? X is 1 and y equal to -1. X not equal to y. But f of x and f of y are equal. So this condition is not satisfied. So f is not 1, 1 here. Okay. So what it actually says is whenever a square terms come, so both 1 and -1 or both the positive and negative real numbers means one real number a and its negative counterpart -a will map to the same point, right? So whenever an x square terms come, this f of x will not be a 1, 1 number. Okay. If x square terms come, then f of x will not be a 1, 1 number. Clear? Clear why it is not 1, 1? Anyone has doubt? Any
Yes,
doubt
clear,
here?
madam. Yes, yes,
Okay,
no
okay.
doubt. No doubt. Okay. It is not
Now-
1-1.
Okay, now what about ontoness? Now let's go to ontoness. Is this onto?
Yes.
Okay. Can you say any element which is mapped to 10, sorry, minus 10? Okay, let me explain. The given f of x is 5x square minus 8. Correct? This is always greater, this 5x square is always greater than or equal to 0, right? Because x square is always positive. Okay, so this 5x square is always greater than or equal to 0. So this 5x square minus 8 should be greater than or equal to minus 8. Correct? Any doubt here? So what it actually says is f of x is always greater than or equal to minus 8. Whatever the value x, whether x is negative, positive or 0, whatever the value I am giving, this f of x is always greater than or equal to minus 8. Is this okay? Is this okay? Last statement. Everyone? Now, provided this statement, now can you say whether it is onto or not? See, the image is always greater than or equal to minus 8. If I am taking some minus 10 or something, f of x cannot be minus 10, right? F of x, we have f of x greater than or equal to minus 8. Suppose I have some x in R such that f of x equal to minus 10. So this condition 1, this f of x greater than or equal to minus 8, we already have. So if there exists an x such that f of x equal to minus 10, then we should have f of x equal to minus 10 is greater than or equal to minus 8, which is wrong, right? This condition is wrong. So this statement is false. Okay, so for any real number less than minus 8, we cannot find a x in R such that f of x equal to that real number. So what this condition says, this is not onto. Is this clear for everyone why it is not onto? Any doubt here onto condition? If you have any doubt, you can ask. Actually, to check the 1-1 onto condition, I will suggest you to solve so many problems. If going through the so many problem, you will understand how it works, like why it is onto or why it is not onto, and the same way 1-1 and you will get you will understand what class of function will be 1-1 and what class of function will not be 1-1, and same for onto. So just take some function from different domains and different codomains and just solve the problem for 1-1ness and onto-ness. Check whether it is mapped, whether the map covers all the codomain, then it is onto. And if distinct elements are mapped to distinct images, then it is 1-1. So only thing is you solve the problem. Solve the problem. So many problems solved. Then only you will understand the concept. Tell again means this one can, which one do you want to repeat? Which part do you want to repeat? Is this a on to? Okay. Okay, on to of this question, right? Okay, let me so the function is given as okay, the function is given as f of x equal to 5x square minus 8. Okay. Suppose f is on to. So we are thinking that f is on to. We don't know. We are taking f is on to. Okay. Now from the function f of x, I have an intuition that this 5x square is means if x is positive, negative, or 0, this x square is always positive, right? And 5x square is always positive number. Okay, it will be not positive, it can be greater than or equal to 0. So this 5x square is always greater than or equal to 0. And 5x square minus 8 will be greater than or equal to minus 8. So this, what I am thinking is this f of x is always should be greater than or equal to minus 8. But I just want to prove that. So I am taking an element, the function is from R to R. Okay. If f is on to, every element in this R should have a pre-image here. So I am taking an element minus 10 in R. And as I am assuming there exists some y in this R. That means a y from this R such that f of y equal to minus 10. Clear? So, but by definition, what is f of y? 5y square minus 8. That is f of y is 5y square minus 8 equal to minus 10. Is this okay? This implies 5y square equal to minus 10 plus 8 equal to minus 2. That implies y square equal to minus 2 by 5. Now, is there any real number y such that y square equal to minus 2 by 5? Does that exist?
No, madam. No.
No, because for any real number, the square is always positive. So y square equal to minus 2 by 5 means y is a complex number. But our domain is just real number, right? So y does not exist. Such a y does not exist in R. Okay. So if I am taking a minus 10 in R, I am not getting any y such that f of y equal to minus 10. There does not exist a y such that f of y equal to minus 10. What does that mean? Minus 10 does not have a pre-image in R. That means minus 10 does not have a pre-image. What does that mean? F is not on. Clear?
Yes. Hello. Okay.
Yes. Okay. The question is, by both results, it is not 1, 1 and on 2. So far, can we conclude as not a function? No, we cannot. Because a function can be there, which is not 1, 1 and not on 2. Like not 1, 1 and not on 2 does not imply it is not a function. For example, f of x equal to x square. We have done so many examples of x square, f of x equal to x square. F of x equal to x square is not a 1, 1 map and not an on-to map from R to R. But it is obviously a function. Okay. Is that okay? For see, 1, 1 on 2 is just a condition. Yeah, okay. So any other doubt?
Madam,
if a function is 1, 1 either onto, so we can say that function is
Function is? Can you repeat the question?
if the function is 1, 1 or onto, then can we say that exists in that domain?
What exists in domain? I didn't get you. So function is 1, 1 or onto then? Can you repeat the question? Your doubt?
Hello, my question is for function to be true, it should be satisfy 1, 1 or onto or both.
No. Like some assignment, like a map from A to B. First of all, we will check whether it is a function or not. Then only we will go to one-oneness and onto-ness. This one-oneness and onto-ness we will not check directly. First of all, it should be a function. Then we will check 1, 1 or onto. It can be any possibility. It can be 1, 1. It can be onto. It can be both 1, 1 and onto. It can be neither 1, 1 nor onto. So function is the first definition. The subclass of functions are 1, 1 function, onto function, bijective function, and so on. So, okay, is that answer your question?
Okay.
Yeah.
Okay. Thank you.
Madam, one more doubt, ma'am.
Yes.
About relation. Suppose S is a set containing the elements 1, 2, 3.
Yeah.
For that set, the relation contains the pair 1, 1, 3, 3, 1, 3, and 3, 1.
1 minute. S equal to 1, 2, 3, and relation is?
Relation is 1, 1, 3, 3,
3,
1, 3.
Yes, 1, 3.
And 3, 1.
3, 1. Yeah.
This is a relation because the element 2 is not included in the relation.
Yeah, it is relation, obviously, but it is not a reflexive relation.
Madam, my doubt is this is reflexive or not?
This is not reflexive because
Why,
2 is not there. Reflexive means for every element in S, for every A in S, A should be in the relation. It should be true for all A. For 2, it is not true here, right? So it is not reflexive.
This is one of the relation. Reflexive. This is not reflexive.
Yeah, this is not reflexive. Reflexive means first of all 1, 1, 2, 2, 3, 3 should be there. After that, some extra element can be there, but these 3 elements should be there.
Okay, madam. In R, the condition all conditions are satisfied in R. Except 2.
Yeah.
But all the other all reflexive 1, 1 and 3, 3 satisfy the reflexive condition.
Yeah.
And transitive condition also satisfied.
Yes.
Symmetry condition also satisfied in R.
Yeah, symmetry also satisfied.
But this is not reflexive.
Okay. This is not an equivalence relation because it is not reflexive.
Okay. So we have to consider all the elements on the set. Yes.
Yeah. Yes. Then only we can say reflexive. So for all the elements, the pair A should be there.
Okay, madam. Okay, madam. Thank you.
Yeah. Any other doubt?
No, madam. Next exam you can take.
Sorry, any doubt? No, right? Okay, if anyone has doubt, you can ask. Otherwise, you can leave. I think we can stop the session. It's already 8:10. So, yeah, thank you everyone for joining.
Hello.
Yeah.
You can take extra example in few minutes about the assignment.
Which example?
from the assignment.
Assignment.
Similar to assignment. Similar to assignment.
Okay, actually, I haven't checked the assignment. Like whatever the question I have solved, it is similar to assignment only, actually. The same kind of questions. So the exact question I cannot solve. So if you have doubt, like
No, ma'am. I mean that on the permutation, on this, all we have covered, I think. Because I think, wait, I have written from this. From the enumeration, enumerable or finite or countable set, we didn't cover this. Permutation we covered. Permutation we covered. From the finite or countable set, we didn't cover any example.
Okay, finite and
From the group also we.
Yeah, group, I think one question we solved, like just checking the group. And finiteness, okay, I will just. So, what is enumerable or denumerable? So, if there is if A is enumerable, if there exists a bijection from N to A or N A to N, right? What was the exact definition? Yeah. If there exists a bijection from N to A, or if there exists a bijection from N to A, obviously there will be an inverse from A to N, which will also be a bijection. So equivalently, we can say there exists a bijection from A to N also. So for example, okay, I will give one set A equal to set of all 2n such that n in n. Okay. So what will be the elements in the set? Can you say what are all the possible elements in the set A? N varies in the natural number n. So we need to take set of all 2n's. That is 2 into 1. Like n in n means n equal to set of all 1, 2, 3, and so on. So we need to multiply each of the element with 2. So it is 2, 4, 6, 8, etc. Like this it will go. Okay. So now my set is here. Can you find a bijection from N to M? Can anyone say a bijection, an explicit form of a bijection? Then we know that it is 1, 2, 3, etc. Okay, I am defining the map F as F of n equal to 2n. Okay, so what we will get? 1 will be mapped to 2. F of n equal to 2n. So 1 is mapped to 2 into 1, 1. And 2 is mapped to 4, 3 to 6, etc. So this first row contains the elements from n. This covers all the elements from A. Okay. So clearly, this is a bijection, right? F of n equal to 2n from n to A is a bijection. You can check the condition 1, 1 and ontoness explicitly. Okay. From just by seeing, you can see the map. 1 is going to 2, 2 to 4, 3 to 6, 4 to 8, etc. So for each element, there exists exactly one element. That is same as it is 1, 1 and onto. That means it is a bijection. Okay. So we got a bijection from N to A. So we can say that A, set of all even natural numbers, is enumerable. Okay. This is a enumerable. Okay. Also we can say it is countable. Countable means either enumerable or finite, right? either finite or enumerable. Here it is enumerable, so implies it is countable also. So what does the finite set means? If I am having a set A equal to some x1, x2, etc., xn, means I can list the elements. Means the number of elements in the A is finite. Here number of elements in A is n, right? So this A is finite. Okay. So we got what is finite and what does the countable means? Countable means either enumerable or finite. Here A is finite. So A is countable also. Okay. So in the same way, we'll just give you it as an exercise. You can try. Set is enumerable. So what does that set is enumerable means? So there exists a bijection from n to z, or there exists a bijection f inverse from z to n. So one thing is we need to find the bijection, how the map n to z or z to n is mapped. For example, okay, I will not give the explicit form of this map f. Okay, for example, suppose n equal to 1, 2, 3, 4, 5, 6, etc. It is going, and z is so a common way or a standard way to find a bijection from n to z is, it is like this. 1 will be mapped to 0. Okay. So here elements in n and here elements in z. Okay. Next element is 2. 2 will be mapped to 1. And 3 will be going to -1. Okay. 4 will be going to 2. So here in this right side, what we are doing is we are giving a nice way to count the elements of z. So we will start with 0, then 1, and its inverse part -1, then 2. Next it will be -2. So 5 will be mapped to -2, etc. So in this way, we can find a bijection from n to z. So such a bijection f exists. So basically, we will say the cardinality of n and the cardinality of z are same. So f from n to z is here. So in this way, z is also enumerable. So I will suggest you to find the, okay, there exists an explicit form for this function. Here you can see that all the even natural numbers, 2, 4, 6, etc. is going to positive integers. Okay. And 1 is going to 0. And all the other odd natural numbers going to negative integers. So using this property, you can just see how the map is going. Okay. So 2 is going to 1 means 2 is going to 1 means x is going to x by 2. Okay. If x is even, x is going to x by 2. That means 2 is going to 1, 4 is going to 2, 4 by 2, 2, 6 is going to 3. So, okay, I have given the explicit form of the function where even natural numbers are mapped to z. So, in the same way, how the odd natural numbers are mapped to this negative integers. Just see. Okay, exercise. How will be the map for? So if you can explicitly define the map, then you can explicitly write the function as f of x equal to x by 2 for x is even, and f of x equal to whatever the explicit form you are getting for x is odd. So that will be a bijection, and in that way you can say set is enumerable. Okay. So how will be the map from odd natural numbers? Okay, just try this exercise. It is not so difficult. If you want, you can refer Rudin's text. Rudin's real analysis text. I think it is all there. If you want, you can just refer. I think solution is there also. Okay. Otherwise, you can just Google it also. It is a very standard mapping. So, okay, this is about this enumerable. I think there will be not much question about this enumerable, denumerable, just to check whether the two sets are finite, whether the given set is countable and so. So, okay, this is all about enumerable, finite and all. Okay. Any other thing you want to explain?
Okay, the time is too much.
Yeah, is this clear? Last exercise or
Yes,
example?
yes.
Okay.
Yes.
Okay, just go through the questions and solve all the questions. If you have doubt, you can post in the forum also. Or you can ask in the next week also. Next week again, we will have the live session for the next week 3 content. Okay, if you have doubt, you can ask. Otherwise, we can stop the meeting. Any other doubt? Okay. Okay, then let's close the session today. What is next week? I think week 3 is already released in the portal. You can check that. Week 3, actually, I haven't gone through the week 3 content. Okay, week 3 will start with the group and the properties, theorems. Okay, mainly it is concentrating on group. So, okay, before coming to the live session, please try to go through the content of the week 3. So it will be easy for you to understand, and try to solve the assignment question also. Okay, then let's stop the session. Thank you everyone for attending. We will meet in the next week.